everybody! This is the third chapter and first part of the crystal clear electronics videos, where we introduce you to the topic electronic symbols. I am Bárány Bence, a third year electrical engineering student. I've always been interested in electronics, but I really got into it when I was in high school and built my first circuits. I didn't design them myself, of course, but followed the circuit diagrams I made using the symbols we are going to show you in this chapter. I also like to work with analog circuits, but I am mostly interested in microcontrollers and embedded software development. Our presenter today is Gergely Lágler.
Thank you for the introduction, Bence. Today's chapter is about the electronic symbols, but we will briefly talk about resistors and capacitors.
The third chapter was written by Károly Póka. As you can see, we already prepared some electronic components and tools for you. Gergely, can you talk about why it's important to get to know the electronic symbols as soon as possible?
Our goal is to bring all of our viewers closer to the world of electronics, and we hope that many of them will become hardware designers and software developers. The wiring diagram shows the components of our circuit and their connections. Designing a wiring diagram is one of the first steps in hardware design, but software developers of electronics also need to understand them. For example, I've just opened on my laptop the wiring diagram of one of the electronics that will be used in the Crystal Clear Electronics 2 curriculum. Here, you can see various components, and it is noticeable that the entire circuit diagram only fits on several pages. For example, I will now click over to the I2C Peripherals tab. Here, you can also see a lot of components, and on a separate wiring page, we have included the components for the general inputs and outputs. It's easy to see that without a wiring diagram, it would be difficult to convey so much information to a third party in plain words. In the later parts of the Crystal Clear Electronics chapters, you will also find wiring diagrams in many places, and we want you to see them not as abstract, modernist-style paintings, but as easy and quick instructions. To ensure that the wiring diagram we design can be interpreted by others, we need to use standard notations. Despite the efforts to create a unified system, there are two kinds of standards. One is the IEC, International Electrotechnical Commission, and the other one called ANSI, American National Standards Institute. For the parts included in this chapter, we aim to demonstrate both standards. Let's take a look at the downloaded PDF of the curriculum, how we mark the wires and nodes. On the first diagram, we see 8 components, which are connected with lines that are representing wires. You may have seen very complicated wiring diagrams, where you cannot draw lines without crossing at least 2 or many more. To make the wiring diagram clear, we have to distinguish those parts where wires cross each other and connected, and those where they just cross but are not connected. The markings of the nodes make the wiring diagram clear. It's easier to find your way with them. In some cases, not only the nodes are marked, but the crossings, where no physical connection is made, are also marked with an arch. You can see this in this diagram. We have also summarized the above for you in an explanatory table in the course material. On the left is the node, and on the right are 2 embodiments where we want to represent the unconnected intersection. I tend to use the top one of these because I think it is more transparent and clearer. Let's take a look at what an open circuit is. In wiring diagrams, the open circuit emphasizes that there is no conductor in the marked section, which would ensure the flow of charges, so current cannot flow. At an open circuit, the current is considered 0, and in turn the resistance is considered infinite. In the curriculum, we can also see the symbol of an open circuit. Here I'd like to note that it is rare that we want to draw attention to an open circuit when designing a wiring diagram, so you will rarely see this symbol. We always want to power our circuits from some device. In a lab environment, this is most often a so-called laboratory power supply, which you can learn more about in Chapter 4. If you're not using a lab power supply, you will usually use a DC power supply, a battery cell, or even a battery. This is related to one of my favorite personal items, which is this cordless angle grinder. I love it because it can provide an effective solution to many of our problems. Of course, it's a dangerous tool, so I only use it with safety goggles on.
If I'm guessing correctly, your angle grinder's battery also contains such battery cells which should not be overcharged, overdipped, or stored or used at excessively high temperatures. Fortunately, the battery housing contains a battery management system, or BMS for short. The BMS measures these characteristics and only allows the battery to be used under the right conditions.
That's right, the battery cell is rechargeable due to the materials used, whereas a very similar galvanic cell should not be recharged. However, they are often used, so let's look at the wiring diagram of the galvanic cell in the lesson. These are manufactured in several forms. Its most common form is the AA cell. In most wiring diagrams or schematics, the polarity is not marked with a plus sign. The long line represents the positively charged anode, the shorter one represents the negatively charged cathode, therefore the polarity is clear. In electronics, batteries are mostly used instead of single cells. Batteries are produced from several elements, cells, usually connected in series, which creates a higher voltage level. The battery symbol consists of a series of shorter and longer lines, which represent the cells of the battery. The galvanic batteries derive electrical energy from chemical energy. When used, the materials inside are transformed, and eventually the battery is discharged. Since the electrical equipment are not always operated from battery, other energy sources may also be involved. Therefore, the terms current and voltage source are used more often. The question may arise, what does this mean in reality? Let's look again at the explanation and the circuit symbols in the tutorial. The ideal voltage source is a circuit element with two terminals. It ensures constant voltage between its terminals regardless the current that flows through it. The symbol of the ideal voltage source is a circle with a line across. Based on these, the definition of the ideal current source can be derived. It is a circuit element which drives a constant value of current through its terminals, regardless of the voltage measured across them. The voltage in the wiring diagrams is marked with a U, its unit is volts, and signed by capital V. The current that flows through the circuit is usually indicated with an I in the wiring diagram. Its unit is ampere and signed by capital A. In the following diagram, you can see several voltage and current sources. Some of them are connected to resistors. The voltage and current are usually marked on the schematics for better understanding. Both of them are marked by an arrow. The arrow, which marks the direction of the current, shows the opposite direction of the electron flow. This can be confusing, but it has historical reasons. Nowadays, it is clear that negative charges move in the wires, not positive ones. In case of the voltage, the arrow points from the higher potential point to the lower potential point. In the next episode, we will talk about more exciting symbols, such as the resistor, capacitor, and exotic variations of these.
Thank you for watching us. Don't forget to subscribe, and you can find all the useful links down below. See you!
Bye!